Okay, amazing. I am seeing something else on my screen here, but I'll just trust the process and just go ahead. Hi, everyone. My name is Maxime, and I will be talking today about Iris-Wasm, a framework to reason formally about WebAssembly that we've also used to reason about extensions of WebAssembly. I'll give a big overview of the project, and I'm not going to get into any technical details today. But I'll try to explain what we've used this project for and what our motivations were in defining this. To start off, I would like to take a short second to remind ourselves why we even endeavor to reason formally using proof assistance. That's probably going to be very obvious, but I think it's useful to keep this in mind. A proof assistant obviously is going to be deliver much better results than other techniques like testing. But what is it we're trying to achieve here? I think there are three main goals when reasoning about a programming language. The first one is that you're going to be able to find bugs, typos, imprecisions, places where you need your language to be completed. Because if you've ever used a proof assistant, you know they're very unforgiving. You need a complete proof, and you won't get away with any shortcuts, any missing edge cases. It's also going to force you to define absolutely everything for your entire language, and so you need to have definitions that are precise and that are complete. But even if you are in a case where somehow maybe you've done extensive testing and you're confident in the fact that you aren't going to find any bugs, having these kinds of formal proof is going to encourage people to use your language, because now you're able to define very precisely what kind of properties your language brings. And you're going to be able to prove those properties to a level of confidence that is not possible by mere testing. And then the third point that I have on my slide is here that you're able to verify code in your language, which I think is what most people think of when you say that you are defining program logics for a large language. And obviously that's something that's very valuable, but to me, I like to remember that there are other important reasons why we do this formal work. So if there are all of these advantages to doing formal proofs in proof assistance, why aren't we always doing that? Well, obviously the largest drawback in doing formal reasoning is that it is a huge effort, which requires expertise, it requires time, you need to define everything. You need to know how to formulate mathematical proofs, and you need to know how to do all of those proofs. That takes time. It's not a resource that you always have, which is why you don't always get to do this kind of formal reasoning. But we argue it's really valuable. And one language where it is as easy as it gets to do formal reasoning as compared to other traditional languages where this defining a mechanization of the entire language would in itself be a very tedious step, is WebAssembly, which obviously today I don't need to introduce, but what I'd like to say is what I love about WebAssembly is that it strikes its balance between being a language that is both very widely used, it's not a toy language, it's not an idealized subset of some language that I use to do research, it's an actual thing that people care about. But it also has this full formal specification that makes it relatively more easy to do formal verification on. And that's obviously something that's big in the spirit of WebAssembly, that's why it's been defined this way. So the starting point in my work has been that we realized that code in WebAssembly is organized in modules, and people care about those modules not being able to arbitrarily interact with one another. What I mean by that is that I don't want a module to be able to meddle with another module state unless that other module has explicitly marked something as exported, as shared. And we were wondering if we could formalize this in a proof assistant as a universal contract, and the strategy we've used is to use separation logic. We have used a framework called Iris, which I'm going to show a tiny bit more of how what it exactly looks like in practice. But the idea is that Iris has an implementation in the ROC proof assistant. If you're able to describe any programming language in the ROC proof assistant, then Iris provides you with a logic, a set of program rules that you can use to reason about the behavior of code in that language. And we've asked ourselves whether or not we could use this on an industrial sized language. like WebAssembly. And that's what we've done. We've defined Iris-Wasm a couple of years ago, which is an instantiation of Iris for WebAssembly. I'm going to show very quickly what that looks like in practice. But the big picture is that we have a program logic that you can use to reason about code in WebAssembly. That is the full industrial definition of WebAssembly 1.0. We haven't got 2.0 yet, but that's something that we could probably achieve as a future work. There's one small departure we've made in the way that WebAssembly deals with host calls that was ill-adapted to a mechanization. But apart from that, we're sticking exactly to the definition and not to an idealized subset. We have a logic that is higher order, so you get to have proofs that are proofs of very general statements. The logic is modular, meaning you can reason separately about different functions or different modules and then compose all of the works you've done together to reason about entire traces of execution. We model reentrancy, meaning you can call the host, the host can call WebAssembly back, and you can have these kinds of complex interactions between the host and WebAssembly. And we've defined a logical relation that goes hand in hand with the program logic that allows you to reason about unknown, untrusted code. It's what we call robust safety. And what that means is basically if you are making a call to a function that you don't know, say a library function to a library that you don't trust, you're still able to say some meaningful things about that interaction. How that looks like in practice is that I have resources in my language. These are these little arrow statements that I have on screen now. I have a resource here for global variables that says global variable G points to 42. I've written WG on top of my arrow to indicate that this is a WASM global variable. And likewise, all of the elements of the store are going to have an associated resource for the memories. It's noted with WM. And what I'm reading here is that the memory number M in the store at address specified by the subscript here is pointing to the byte 47 or whatever the byte might be. And then we can write proofs that are going to look like this. If I know that that my variable G points to 42, then I'm able to run this short program that just gets the value of G. And I know that when this program returns, I'm going to get value 42, and I still own my resource, so I'm able to further reason about G later on. In the most general form, it's what I have here at the very bottom of my slide. I have a precondition P. This implies with the wand that is separating the implication that we use in separating logic. I have the weakest precondition for my program E, and that means that my program E runs safely. It does not get stuck, and if it returns, then the value V on its the return value V satisfies its predicate phi, and P and phi are going to be phrased using these resources. So that allows you to reason about code, to verify code if you'd like. And then the most important result that we have is this logical relation that we've defined, which is a mathematical object that is defined in a proof strategy in order to prove these kinds of very strong properties. And the property that we've proved is that if a program type checks syntactically, which is something that is in practice always achieved because instantiation will guarantee this, then whatever input I give it and whatever imports this program does, as long as I'm able to verify that these inputs are valid in a way that I would need to define, then I'm going to be able to run E with those inputs V, and I'll terminate on a value that is also valid. And what this means is that I need to provide resources to indicate that all of my imports are valid, but nothing else, which means if I am calling an unknown function and there is a part of my store that I have not marked explicitly as exported, that is not going to be an import of that unknown code, and that means I'm able to know that that code, that unknown code, is going to run safely, not get stuck, and I don't need to provide that value. So this formally captures local state encapsulation, and is a very strong formal proof that WebAssembly has that property. Now, obviously, WebAssembly we've been using for years now, and so maybe there wasn't too much doubt that WebAssembly has this local state encapsulation property. But the thing that we're most excited about with Iris-Wasm is that now we can use it as a departure point to reason about new variations of WebAssembly that maybe we don't know as well as WebAssembly. Maybe we don't have as strong confidence that these languages have whatever properties we'd like them to have. Oftentimes, when you create a new version of WebAssembly, you can think of it as the intersection between WebAssembly and a new feature. And because Iris is, just like WebAssembly, a very vibrant research ecosystem, that new feature has oftentimes already been studied in the Iris program logic. So our thought was that maybe we can, in that case, try to massage together all of these existing projects to get a program logic, a logical relation, establishing a universal contract on those new versions of WebAssembly, on those new extensions that we are now saying interesting things about, where maybe it wasn't as clear as before. I'd like to stress here that even though I have this presentation as a Venn diagram that might make it look like this is as simple as taking the intersection of existing works, there is a lot of work involved in actually making this work, as probably should expect it when you're working with these large industrial size definitions. But we argue it's worth it because everybody in this diagram will then win something. For the WebAssembly community, that's what I mentioned at the beginning of my presentation. We're going to find bugs, we're going to validate the design of our new extensions, and we're going to encourage people to adopt these new extensions by telling them exactly what they're getting out of it and giving them the strong confidence in the properties that they are getting. The Iris community, from the logic perspective, gets to see the logic exercised on a very large scale and highlight some needs, some things that work, some things that don't, some things that should be improved. And then the new feature community gets that feature studied at a real life scale. And here I'd like to conclude my presentation by giving 3 examples of how we've achieved this in the past on extensions of WebAssembly. The first such project was Iris-MSWasm, an instantiation of Iris and an extension of Iris-Wasm for memory-safe WebAssembly, a version of WebAssembly that uses capabilities, hardware capabilities, as a way to access memory. Instead of having a pointer, I have an unforgeable token of authority that allows me to access memory. And what that means is that all of a sudden I'm able to share at a much finer grain. I don't need to share my entire memory or nothing. I can share specific locations because only people who hold a capability which cannot be forged, cannot be accessed by unprivileged operations are able to access my memory. So we are able to provide a full mechanization of the logic, a full program logic, and a full logical relation that encapsulates a much stronger contract, which is robust capability safety. So if we look at my theorem from before, I have almost the exact same phrasing here, except my definition of this V is a bit finer, which means that when I say that I need all the imports that my unknown, untrusted program has access to are valid, this means that I need to provide them with resources for all of the specific addresses that they'd like to import, not entire memory. So we have a much stronger property here where you're able to share at a finer grain. And this is a work that we're really excited about because MSWasm is not something that has been extensively tested yet. And now we have some formal proof that some of these things actually work and a formal statement of exactly what it means that we have this stronger safety guarantee. Another work in progress that's nearing nearing completion is Iris-Wasm effects and an extension of Iris-Wasm to Stack-Switching, the version of WebAssembly that has effect handlers. And for that, we've taken inspiration from an existing logic in Iris called Hazel. We've now defined a full mechanization of the language with a proof of type soundness, and we've been able to define a modular program logic, which is a big deal when you have effect handlers because it means we're able to reason about functions that do perform effects in isolation and then compose all of our proofs together. And the way we've done this is by introducing this protocol in our logic. So we have a slightly more complicated weakest precondition statement here that takes into account when I'm performing an effect, I might not be able to reason modularly if I don't treat the effects separately. The last work in progress that is using Iris-Wasm is Iris-RichWasm, an extension of Iris-Wasm for a version of WebAssembly that has a richer type system, which allows us to have some much finer grained proofs, especially when you're reasoning about the interaction between a GC language and a manually managed memory language. If you have these two languages interacting, you could compile them both to RichWasm, and then RichWasm compiles down to WebAssembly, and we're trying to use Iris-Wasm to prove safety of that kind of a compiler, which is a very exciting work, and that we look forward to bring to completion. To conclude, Iris-Wasm shows that machine check proofs are possible even on languages like WebAssembly that are industrial scale. And we would love to see a lot more of that because of all of the positive things that this kind of reasoning brings. We think Iris is an ideal tool to do this, and in the case of WebAssembly in particular, we think Iris-Wasm is an ideal starting point when you'd like to reason about these extensions of WebAssembly. Two works in progress are the works I've just mentioned on stack-switching and on RichWasm that are at various stages of completion. In maybe longer-term future, we'd like to investigate how Iris-Wasm could work together with SpecTech, or would we be able to use the kind of automation that SpecTech allows and brings to the table while doing these kind of formal program logic proofs in Iris-Wasm. Here's the Venn diagram again on exactly how Iris-Wasm works and how you're able to get this trophy in the center in order to boost your own exciting new variation of WebAssembly using formal reasoning tools. Thank you very much.
You may not be able to hear it, but we just applauded you. So
thank you.
A little into the break time. Maybe we'll have one or two questions if anyone has something they'd like to bring up. I have one question. Iris is famous for doing concurrent reasoning. Clearly, you're not modeling concurrency in WASM yet. Have you looked at that at all?
So Iris is famously a very powerful tool to reason about concurrent logic, but there are a few examples of Iris being used to reason about sequential languages as well, and this is certainly a big one of those. In the future, if we were to reason about a concurrent version of WebAssembly, in that case, we already have all of the machinery in Iris to reason about that, and in the stack switching project where we reason about Iris with effect handlers, we have used this machinery in order to reason about examples where you would emulate concurrency using effect handlers. So we have an example illustrating Iris-Wasm effects that implements a coroutine library where you would have this kind of concurrency, and it has come in helpful that we already have a number of works on how you would use Iris to reason about those. So we think that's definitely a strength for Iris-Wasm moving forward.
That's great. Thanks so much. I think we'll go to the break now, but thank you for joining us, Maxime. Let's thank Maxime one last time. All right, we're now going into our break. Thank you for joining us, Maxime.